Welcome to the fourth presentation in Unit 3 entitled Connect the Dots. It says you can't connect the dots by looking forward. You can only look at them connecting or look you can only connect them looking backwards. So you have to trust that the dots will somehow connect your future. You have to trust in something, your gut, destiny, life, karma, whatever. This approach has never let me down and has made all the difference in my life. Steve Jobs. So, the first thing we want to do is we want to look at the learning goals. And the learning goals for this particular presentation are that students will be able to relate the chemical period, that's the row on the periodic table, to the number of electron energy levels. You should be able to relate the valence structure of an atom to the chemical period, that's the column. And that you should be able to, this should be the chemical family. And that you should be able to generate Lewis dot structures for an atom. Okay, so here's what we know. We know there's a consistent pattern of protons, neutrons, and electrons on the periodic table. And we know the periodic table was developed to show the trends in atomic structure. We also know that elements that are in similar chemical families have the same structure or have the same properties. So here's what we learned in the lab. Elements in the same column have the same outer number of electrons. We called those valence electrons. And elements in the same row use the same outer electron level. So everything in the same row has 4 energy levels, or 5 energy levels, and everything in the same column has the same number of valence electrons. So when we look at electrons, remember electrons are equal to the number of protons in an atom. Electrons travel very, very fast out in orbitals outside of the nucleus. And electrons are negatively charged. So let's review from the atoms. Next, if we look at valence electrons are the electrons in the outermost energy level. So this right here is phosphorus. Phosphorus has 15 electrons, but it only has 5 valence electrons, because in its outer orbital it has 1, 2, 3, 4, 5. In a valence electron, you only consider the outermost electrons in the valence shell. Everything else is what's called an inner electron. These inner electrons, although they're there, are not the reason why chemical reactions occur. This particular atom has 3 energy levels: the first, the second, and the third. In this case, the third electron shell is the valence shell. If you were to look at the periodic table and energy levels, the chemical period refers to the row on the periodic table. The chemical period of the row is the same number as the number of shells. 1, 2, 3. We find phosphorus in the third row because it has 3 electron shells. Now each energy level can hold a different number of electrons. For example, in the first electron energy level, it can hold 2 electrons. In the second one, it can hold 8. In the third one, it can hold 18. And in the fourth one, it can hold 32. And so on and so on. It escalates as you move up. So whenever we say the first shell can only hold 2. That's why things like hydrogen and helium are happy with only 2 electrons, because they have a full valence shell. Whereas most things need 8 electrons in their valence shell in order to be satisfied. And there are also things that need 18 when you start to move down the periodic table. So if you look for krypton, in the first electron shell, there's 2 electrons. In the second there's 18, and in the second there's 8, in the third there's 18, and in the fourth one there's only 8. Now, I could put up to 32 in there, but because I don't need 32 electrons, I only put as many as I need in there. Whenever you look at the periodic table in valence electrons, the chemical family refers to the column on the periodic table. The chemical family or the column have the same number of valence electrons. Here you see phosphorus and nitrogen. Phosphorus and nitrogen are in the same chemical family. And if you look, nitrogen has 1, 2, 3, 4, 5 valence electrons. It has 5 valence electrons even though it only has 2 shells. Phosphorus has 1, 2, 3, 4, 5, which means it has 5 valence electrons, and it has 3 shells. So what that means is that nitrogen is above phosphorus, where nitrogen is in the second row and phosphorus is in the third row. The fundamental A1 says write the definition with the terms below. An inner electron refers to one that is not in the valence shell. So if we were to look at something like lithium, lithium has 2 protons in the first shell and 1 in the outer shell. So because of that, it would have 1 valence electron and it would have 2 inner electrons. How many valence electrons does lithium have? 1. Determine the total number of electrons, then classify each as a valence or inner electron for bromine. Whenever we look at this, though, the first thing that we're going to have to look at is we're going to have to find bromine on the periodic table. So when you look at the periodic table, you have to remember that bromine is the element Br, and it's in group 17. So because of that, we know that it is going to have 17 valence electrons. When it has 17 valence electrons, and it has an atomic number of 35, well, that lets us know that there are 35 total electrons. And because it's in group 17, I know that there are 7 valence electrons. So that means that there are going to be 28 inner electrons and 7 valence electrons. It says an element has been determined to have 3 energy levels and 2 valence electrons. Write the nuclear symbol notation for the most common isotope. So if we were to kind of scroll in right here, we know that it has 3 energy levels, and we know that it has 2 valence electrons. So because of that, we know it's going to be in group 2. So that means it's going to be magnesium, and magnesium is 24. So when we look at this, we can write it as Mg, 24, and 12. And this would be the nuclear symbol notation for the most common element when it has 3 energy levels. Third row, 1, 2, 3. 2 valence electrons, second column. Second column, third row, that means it's going to be magnesium. Now, valence electrons and reactivity. Atoms can react to form new compounds, and we're actually going to explore this in a lot more detail in future units. But whenever you look at them, only the outer electrons can react with another atom. If you look, there's no way for these electrons in hydrogen to actually access the inner electrons of oxygen, because these electrons on the outside get in the way. So because of that, only valence electrons will determine the reactivity of an element. That's why whenever you look at the columns, they have the similar valence electron structures as you move down the periodic table. Because of that, we want to create something called a Lewis dot structure. Lewis structures are used to show the number of valence electrons that are available for an atom. Basically, what a Lewis structure is you write the chemical symbol for an element, and then you fill in the valence electrons. The problem with it is the first 2 valence electrons go on the same side. So this right here is not a good example for beryllium. Instead, beryllium should be beryllium, Be, and then you have to put the first 2 electrons on the same side. Now there's a reason for that as far as filling orbital shells. We're not going to get into that. The most important thing is that the first 2 electrons go on the same side. Then you spread out the rest of the electrons one at a time. So if you look for boron, I put 2 electrons on the same side. The next one goes here. When I go to carbon, 2 electrons on the same side, and then the next 2 are on different sides. Nitrogen, 2 electrons on the same side. Nitrogen, 1, 2, 3. And then at that point, if I needed more electrons, I can start filling them in to pair them up. So it says, why do inner electrons not matter in a chemical reaction? And the reason is the inner electrons have no proximity, which means they're not very close to other atoms. So it's because of the physical location of these electrons. Whenever you look at this, there's no way that this chlorine atom can access the electrons that are very close to the nucleus, because there's too many other electrons in the way. So it's the outer electrons that are available that allow them to react. It says, how many valence electrons does the atom below have? Remember, a Lewis dot structure tells you the number of valence electrons. So we'd say 1, 2, 3, 4, 5, 6, 7. So we'd say this is chlorine that has 7 valence electrons. And also that tells us that it's going to be in group 17. Next, it says to draw the Lewis dot structure for sulfur. So we go to our periodic table, and we know that sulfur is an S. And then it says, okay, sulfur is in group 16. Since it's in group 16, remember that tells us that we have 6 valence electrons for sulfur. So I draw my first 2 electrons. They go together. And then I fill in. I say, so I've used 2. So I've got 4 to go. And then you have a total of 6 valence electrons. Now, if you drew your sulfur a little bit differently, if you drew it something like this, that is perfectly acceptable as well, as long as you have a pair of electrons and then a pair of electrons, and then the other ones are single. Finally, it says atoms with 8 valence electrons are considered to be stable and do not react with other elements. Draw a Lewis dot structure for argon and explain why argon won't react. Well, if you look at argon, argon is in group 18. Because it's in group 18, it has 8 valence electrons. And since it has 8 valence electrons, it looks like this. And earlier in the passage, it told us that atoms with 8 valence electrons are stable. And the reason why is atoms want to have 8 electrons around them to satisfy what's called the octet rule. Since argon already has 8 valence electrons, it doesn't make any sense for it to bond or share or give away or take an electron from anything else because it's already met the standard to satisfy.